In part 3 of the tutorial, we're going to focus on nanoparticles with spheres. We pick up from part 2, in which we had created a system where light is incident in air. It passes through a layer of gold nanoparticles of diameter 24 nanometers, also in air, and then it passes into a medium of glass. The light comes in roughly at an angle of 0, and it's incident on the slide. Recall that in the last example we had used a nanoparticle with shell thickness of 0. Now we're going to set this to some value, but let's talk about what we mean by a nanoparticle shell. Typically, the nanoparticle shell refers to a gold core sphere covered by a concentric sphere of a width or a thickness, and the core is defined by a radius r1 and an index refraction n1, which is the index refraction for gold. R2 corresponds to the shell's distance from the center, and it's characterized by a material N2. So the shell is a homogeneous material. The other case is when the shell is a heterogeneous material, for example a biofilm or proteins bound to a gold nanoparticle. PAME can also handle this system, but we're going to talk about that in part 4. So to begin, let's make a concentric shell on a gold particle, and for N2 we're going to use glass. So this represents a gold particle with a silica coating. Come to core shell composite mix and choose shell material. This will bring up the material adapter, and we're going to pick dispersive glass. Recall dispersive glass is the default value for the cell mirror model. Now this shouldn't change anything because the thickness is still 0. If I come to shell material, you see that yes, indeed, it's dispersive glass. When I change the shell thickness to 5, it's going to change the permittivity. So a 5 nanometer shell affects the permittivity. It's more constructive to look at the scattering cross-section, or the extinction cross-section of the individual particle. This system has an analytical solution in me theory, so I can solve it exactly for various values of N2 and R2, which is what you're looking at here. When we set the shell thickness to 5, you're going to see that the peak here shifts to the right. This is called the plasmon resonance shift, and it's a well-known effect that occurs when you change the local vicinity around the core of a nanoparticle. Changing it to 15, for example, induces a larger shift, and it begins to induce scattering effects. Likewise, this has an effect on the overall reflectance of the film. So if I change it back to 0 and I update this, it shifts back to the left. Now let's ask ourselves, what's the relationship between this, which is the analytical solution to an individual coated sphere, and the reflectance, which is from the ensemble? Well, I'll show you how PAME computes these, or what their relation is to one another. Essentially, PAME is computing the reflectance from a slab of homogeneous materials. The layer of gold nanoparticles also has to be treated as an homogeneous material, and this is done through an effective mixing theory. The effective mixing theory that we used last time is the Maxwell-Garnett theory with Garcia's modification. So Maxwell-Garnett takes a film like this and it homogenizes it to a material that has the index of refraction is based on a mixture of all 3 of the materials. That would be air, the coating N2, and the gold N1. So to go from here to here, that's done in this piece that we looked at in the last tutorial. Effectively, this is performing this. But the Maxwell-Garnett theory doesn't understand a particle with a shell, it only understands a particle, i.e. one spherical inclusion. And so to treat a shell particle, there's another approximation that's made. It's called the complex particle approximation. Complex particle takes a core shell particle and it defines an equivalent particle that has a radius r3, which is generally somewhere between r1 and r2, and an index of refraction n3, which is generally somewhere between n1 and n2. So we ask ourselves the question, how do we believe that this particle and this particle are the same? Because the computation here is based on this particle. So I came up with a theory of how you could justify this. I'm going to run that by you. If you think that the theory is wrong, feel free to bring it to my attention, because I haven't seen this employed before. So here's the logic we're going to use. Because we can use Mie theory to calculate the optical properties of these nanoparticles exactly, and we can use Mie theory to calculate the optical properties of a core particle, characterized by R3 and N3, I'm going to argue that if the extinction cross-section of these is identical, then using this in the effective mixing theory is no different than using this in the effective mixing theory. That's my argument. And how do I prove that? Well, if I come to the full double cross, what that's going to show on the left is the extinction cross-section computed analytically for this particle. And here it's showing the extinction cross-section from Mie theory computed for this particle. And I would argue that if these are identical, then you can use them equivalently. If we pick combined, it's going to overlay them. Now, oops, my shell thickness is 0. When I set the shell thickness, you're going to see that these no longer are exactly the same. The red corresponds to the equivalent particle, and the blue corresponds to the full solution, the sphere shell. And in the core shell composite, there's a couple parameters that we can use to tune the equivalent particle calculation. So you can see how the equivalent particle's optical properties, its extinction cross-section, starts to deviate as a function of some of these scaling parameters. But that's a pretty close overlap. So I'm going to make the argument that we can use this particle instead of this particle because they have almost identical extinction cross-sections, right? And that's what's happening in the calculation of the reflectance. So please keep that in mind whenever you use calculations based on the ensemble that rely on some characteristics of the individual extinction cross-sections. In part 4, we're going to talk about how to address nanoparticles with a heterogeneous shell. Thanks.